Tired of your target being too far? Try the new Obliterator-Inator. The latest in patented United States technology. Obliterate anything from anywhere.
Since this is a 32 megajoule rail cannon, we can just use that as our energy and solve for kinetic energy. If we isolate velocity here, then we can find the velocity of the projectile after it leaves the barrel. Now here we can just plug in all of our variables. The railgun has 32 million joules of energy and our projectile weighs 3.2 kilograms. The velocity after it leaves the barrel is 4,472.14 meters per second.
With a solid
3.2
kilograms of tungsten
and 4,400 meters per second of speed. We can find that from our rest position, the acceleration in the barrel is 1,100,000 meters per second squared.
And if we plug that into the equation, we end up with
3,700,000 newtons of force.
that's enough to punch a hole through steel. Let me walk you through the blueprints. Inside of this baby we have two rails with magnetic fields. One's positive and one's negative. In between those rails is the armature, which carries our payload, a cute little tungsten dart. Now the armature is also conductive, which means it can conduct the current that's being passed from the positive through it into the negative rail. This uses the Lorentz force, which accelerates the armature and the projectile. What's the Lorentz force, you ask? This nifty equation here. So to put it simply, the high velocity particles create a magnetic field that propel the armature out, and once it's out, look at it go! It's almost like it has a range of
200 kilometers.
That's 10 times better than your average ship gun. How do we figure?
Well, we're gonna look at this like a cliff problem, where the angle of the projectile being shot at is 45 degrees. Now, in order to get T down, we're gonna need the maximum height that the projectile reaches. Luckily, we already have all the variables needed. Now we can calculate T down by using the simple formula of the square root of twice the max distance divided by gravity. T-up's formula is even simpler than T-down, and as you can see, we also get a fairly similar result. That's because the only difference is the 10-meter height difference between the ground and where the projectile was fired. And now we just have to add the times together, and wow, you can see the projectile stays in the air for around 11 minutes. Now it's as simple as multiplying the horizontal velocity, because that doesn't change, and the total time it stays in the air. And as you can see, wow, we get a whopping 2,000 kilometers.
And once it's on the ground, it keeps on going. Assuming you're on the street, the coefficient of friction between the tungsten and the asphalt is 0.7.
Now for when the projectile lands on the ground, it's going to be skidding across the pavement. So for this we have the force of friction against the streets, and then we have a force applied, which is going to be simulating the resistance from the debris it's going to be creating and running into. Now the coefficient of friction between the asphalt and the tungsten is 0.72. And for the force applied, both the mass and the acceleration of the debris is going to just be assumed. Now we have a negative acceleration of 43 meters per second squared. This is going to slow the projectile down until it reaches zero velocity. And when it does reach zero velocity, we see that it's moved an extra 230,000 meters. And now adding this distance on the ground and our distance in the air, we now get a total of the projectile's distance of 2,300,000 meters.
Call 1-800-123-4567 for your railgun today. That's 1-800-123-4567 for your railgun today.